Hello guys, I hope you are doing good. Welcome back to another session of Mold Design using SolidWorks. In this session, we will be learning about machine tonnage, which will be a very short topic, and then we will mainly focus on the entire review process of plastic parts done during DFM, and then we will be covering the defects that can occur during mold design process. Now let's look at the concept of tonnage of injection molding machine. The pressure with which the molten material is injected in the injection molding machines is very high. In most of the products, the injection pressure is around 4 to 5 tons per square inch, and in some cases it can be much higher than this. So to ensure that the core and cavity do not get separated due to this high injection pressure, we have to provide proper clamping for the mold. The amount of clamping force provided by the clamping mechanism is decided by the tonnage of the machine. So for example, if we have a 100 tonnage machine, then that basically means that 100 tons of clamping force is provided by the clamping mechanism. Now it's probably easy to imagine why we can't have a very low clamping force. If the tonnage of the machine selected is very less, then the core and cavity will get separated when the material is injected and result in flashes. However, we also can't use machines with very high tonnage values. If the clamping force for the mold is too high, then it can cause defects like burns, shots, and gloss differences. Also, very high clamping force can damage the venting system, inserts, and also the core and cavity block. So the selection of the right tonnage of a machine is also very important. The clamping force can't be kept too low or too high, as both of this will cause issues. The clamping force should be within a certain range to ensure proper injection molding process. The tonnage of the machine is calculated based on the formula projected area multiplied by the injection pressure divided by 1000, where the projected area is in centimeter square and injection pressure is in kilogram per centimeter square. The projected area is the projected surface of the entire model along the tooling direction. Tooling direction is the direction along which your model is oriented and your core and your component will be moving. So let's say the projected area which we found was around 35 centimeters square, and then the injection pressure, if we use ABS material, would be around 500 kilograms per centimeter square. So if we multiply 35 by 500, which will be around 17,500, and then we divide by 1000, which will give you a value of 17.5. So 17.5 tons of clamping force will be required for this machine. But the machines available in the industry come in specific sizes. So a 17.5 tonnage machine might not be available, and in that case, you will select the closest value of the machine higher than the calculated value. For example, if you have a 15 tonnage and a 20 tonnage machine available, then you will go for a 20 tonnage machine. In this section, we will look at DFM in a bit more detail. If you remember, I had covered DFM in brief when we were discussing the departments in mold manufacturing industries. The DFM stands for Design for Manufacturing. So basically, the DFM receives the plastic component for which the mold is required by the customers or the product design team. The review of the product is done by the DFM team in terms of design, manufacturing, and molding aspects, and they also check if all data is available to proceed with the tool design. If they think that there might be some problems in creating the mold for the given product, then they convey that to the customers or the product design team. Here in this slide, I have mentioned the checklist which is followed by the DFM team to ensure that they have all the inputs required for designing the mold. I will be explaining each point in detail in the next few slides. So first we are going to cover the part details. The first point is shrinkage. Whenever the molten material in the mold solidifies, it shrinks. So the actual part size obtained is less than the size of the mold. So the size of the mold is designed in such a way that it takes into account the shrinkage of plastic and gives a part with correct dimensions. To do that, we need the exact shrinkage value for the material that is being injected into the mold. The next point is material. The material here refers to the plastic material used for making the component. And the next is number of cavities. The number of cavities required is also asked from the customers. The DFM team can make suggestions for it, but the final decision comes from the customer side. And the next point is inlet type. There are different types of gates used, and depending on what types of gates you use, there may be some marks on the final products. So the customer are informed on what are the effects of using specific types of gates, and depending on the requirement, the gate type is selected. Type of gates will be covered in detail in a separate session. The next one is surface demands. So the type of surface finish required is also asked to the customers, whether they want the surface to have a textured finish or glossy finish. If the part manufactured won't be visible from outside, then there won't be any need for polishing the tools and providing a good surface finish. For example, if you're watching this video on a PC, then you probably have a keyboard in front of you, right? Now, if you open your keyboard, then you will find many plastic parts inside it. Now, since these parts are not visible from outside, it doesn't matter what surface finish it has. Adding good surface finish requires additional cost and time and must be avoided where it's not necessary. Also, the type of surface finish required will also affect the draft angle given for the geometry. And the last point is there any engraving required? For example, you may see the company logo engraving on many products. So if engraving is required, then the details regarding the engraving is also taken from the customers. Even in engravings, for the length and width of the engraving, there are some standards to be followed. That's because these engravings are milled by CNC machines. So based on the size of the cutters that are available, there are standard engraving sizes. The parting surface is a surface that splits the core and the cavity. In most of the products manufactured by injection molding, you can see a visible mark along the parting surface. So the customers are informed that there will be a mark over here, and is that fine, or should we be changing the parting surface? On the diagram to the left, you can see a parting surface on the product. Even when using sliders, there is a visible mark along the parting line of the product. We have not covered the topic of sliders yet. We have a separate topic on sliders where I will be explaining how sliders work in detail. For now, just know that there are some cases where the core and cavity is not enough for creating a proper mold, and that sliders are added along with the core and cavity to create a proper mold. And the sliders will also leave a mark similar to the parting line. So we have to inform the customers that there will be a mark along this line. You can see the mark due to the sliders on the image on the right. For injection molded parts, there is a visible gate mark present. Most of the times the location of the gate is placed where it won't be visible from outside. But in case it is visible from the outside, the customers are also informed about these marks. You can find these gate marks on the bottom of buckets, pens, bottles, and many other household injection molded products. For the plastic components manufactured, we try to keep the overall thickness relatively constant. This is because if there is a variation in the thickness of the component, it will lead to a non-uniform shrinkage of material as thick sections shrink more compared to the thinner sections. This non-uniform shrinkage causes the component manufactured to warp. In the diagram, you can see that more warpage was observed when there was a higher change in the thickness of sections. However, when we core out the thicker section, which basically means that if we make it hollow, then warpage can be avoided. Coring out can also make the parts weaker, so sometimes ribs are added in the cored out sections to make the part stronger. Usually the thickness values used for plastic components vary from 0.6 mm to 5 mm. If we try to make parts lower than 0.6 mm thickness, then there won't be a proper filling of material in the mold. The material itself will solidify before reaching the ends. This defect also has a name. It is called the short, which will be covered in the defect section. For thickness values higher than 5 mm, gas-assisted injection molding is used. If there are deep holes in a part, then we have to make use of longer core pins to make the deep hole. But using longer pins from the core side results in heat dissipation problems. If heat dissipation does not take place properly, then it will lead to burn marks in the hole region, which is a type of defect. As a rule of thumb, if the length of the hole is greater than 7 times the diameter of the hole, then hole would be considered too deep. To counteract, we split the hole in two parts. So some part of the hole is made using the cavity side and the rest of the hole is captured from the core side. So here in the first diagram, you can see the hole, and this is the core pin used for making that hole. And in the third diagram, you can see instead of making the hole using a single core pin, some part of it was captured from the cavity side. So the cavity will be over here. This hole will be captured from the core side. Another point to note is that in general we try to avoid features in the cavity side. This is because creating these pins for holes in the cavity sides creates more surface in the cavity sides where the material can stick. Sticking of material in the core side is not as big of an issue as sticking of material in the cavity side, because on the core side we have the ejector pins to eject the part. So that's why we make the pins for capturing holes from the core side, and if the length is too large, then we make a pin from the cavity side. When we have the same upper and lower limit for tolerance, for example 10 plus and minus 1, So this means that the dimension of the component can be between 9 and 11, and we can see that both the numbers are equally spaced from 10. So this would be a case of symmetric tolerance. But if we don't have the same limits, for example 10 plus 1 minus 0.5, now the dimension has to be between 9.5 and 11. In such cases, there is a possibility that due to shrinkage, the dimension of the part may go below 9.5. So in such cases, mold is designed for a dimension of 10.25, which is the average of 9.5 and 11, to ensure that the dimension stays within the tolerance. When we close the mold, some air is trapped between the surface. Due to this trapped air, the molten material can't fill the entire mold region and some defects will be found in the finished product. To avoid this, some channels are provided in the mold to allow the air to escape. This process of providing air channels to remove the trapped air in the mold is called venting. Now, before explaining the ejector pads, I will show you what problems might occur while ejecting components with very low thickness values. In this diagram, you can see the thickness of the highlighted section over here is around 1.4 mm. However, the ejector pins come in standard sizes of 3 mm or 6 mm. So if we try to eject the component from this region over here, then that won't be possible because the ejector pin of higher thickness can't move through the core. In this specific case, this issue can be avoided by providing ejector pins over here or here, but that might not be the case in all the situations, and to deal with such situations, ejector pads is one of the solutions we can use. So here in the first video, you can see that we have a component with a low thickness value. Let's assume it to be 1.4 mm. And the size of the ejector pin is 3 mm. So this case is similar to what we saw in the previous slide, and the ejector pin will not be able to eject the part out. Here in the second video, you can see that the thickness of a specific region of the component has been increased to 3 mm. This is known as an ejector pad. By doing this, we can ensure that the ejector pin will be able to easily eject out a part of thickness lower than the ejector pin thickness. Now this would be a good time to explain the concept of undercuts in molding. Undercuts are those features in a part due to which the part cannot be directly ejected from the mold. If you see this figure on the right, you can see the top part is the core and the bottom part is the cavity. Once the material solidifies, you will notice that it is not possible to eject the part from the core due to this highlighted section. This feature is called the undercut. Now there are two types of undercuts available, internal undercut and external undercut. The diagram which you see here is an internal undercut, and this diagram here shows an external undercut. To deal with external undercuts, we use sliders. There is a separate topic where I will explain how sliders work. To deal with internal undercuts, we can use inserts, which I will explain in the next slide. So the diagram which you see here shows an insert and a part. The blue portion is the insert and the red region is the plastic component. The insert is placed at the core side of the mold. When the mold closes, the insert is present between the core and the cavity, and the molten material is injected. Once the material solidifies, ejection pins eject both the part and the insert. You can see a small hole on top of the insert over here. The hole is provided for separating the insert from the part using a screw, and thus the desired part is obtained. Now here we have a diagram showing ejector inserts. Let us assume that we have a part with a large flat surface, let's say for 500 mm or something. So in this case, instead of providing multiple ejection pins to eject the part out, we can use an ejector insert for ejection of the plate. In the given figure, you can see the cross-section view of mold. The green part is the ejector pin, the blue part is the component which is molded, and the orange part which you see is the ejector insert. So this insert helps in distributing the ejection force over a larger surface without the need of providing extra ejection pins. Ejector inserts can also be used in cases where the customer does not want any ejector pin marks on the part. So in that case, an ejector insert covering a large area of the part can be used, which will help avoid the marks that would have been left if multiple smaller surface area ejector pins were used. In the last session, we saw the function of the guide pillar and its role in the overall molding operation. The left side is the core side and the right side is the cavity side. The guide pillar is used for aligning the core and the cavity. You can see there is a projection on the cavity side over here, which is called the guide cone. This is basically for interlocking the cavity and the core region. In the last session, I had mentioned that the core plate thickness is always kept more than the cavity plate, as there is a chance of deformation of the core plate due to the hot injected material. The pressure of the injected material may be around 600 to 700 bars, and to avoid any chance of deformation of the core plate, an additional support block is placed between the bottom moving plate of the mold. Now you might ask, why can't we just keep increasing the thickness of the core plate? What is the need for the support block? It is true that the deformation problem can also be solved by increasing the thickness, but there's a limit up to which increasing the thickness is cost effective. This is because when we increase the thickness, we have increased the material cost for the core plate, and then the length of the holes which need to be milled in the core plate for the ejector pins will also increase. So that is why we use a support block instead. There are two types of cutters used for machining, the ball nose cutter and the flat cutter. Ball nose cutters are used for 3D profiles, and it takes more time for making 3D profiles. So if a parting line is along a 3D surface, then we need to make a 3D profile that would require more time. So that's also one of the reasons why we try to make the parting line in the same plane. When we use ball nose cutters for machining sharp corners, it produces a fillet at the corner, as you can see on the right side of the slide. The creation of this fillet makes it difficult to match the core and the cavity side. So that is why some relief is provided near sharp corners near the mating surfaces. In some cases, if the length of the rib is very long, then it gets difficult to eject the rib from the mold because the plastic sticks to the wall of the cavity. For such cases, we make use of free play inserts. In the first diagram, you can see the cavity region and the part formed within it through injection molding. The yellow is the part and this is the cavity region. Now if the length of this rib is more, then it would be more difficult to eject it out of the mold. In such cases, a free play insert is added. The purple section you see here in the diagram is the free play insert. The free play insert is present in the cavity section. When the material is formed through injection molding, a screw which you see at the top drives the free play insert in downwards direction, which in turn pushes the part out of the cavity. If the length of the plastic part manufactured is more, then we provide multiple gates for the part. The exact length after which we need to provide an additional gate depends on a material property called as flow length. Flow length is the distance after which the molten material will solidify. So for example, in the diagram below, let's assume the length of the part to be around 1500 mm. And let's say we know that for the given wall thickness, the flow length is 250 mm. So here, since the length of the part is more than the flow length, we will have to provide additional gates. So if we think of providing 8 gates, we can check that 1500, the total length divided by 8 would be some value between 180-190 if I am not wrong. And since this value would be less than the flow length of the material, there shouldn't be any freezing of material due to an inadequate number of gates. So this is how the number of gates is selected based on the flow length of material.
Now we will look at the concept of balancing of mold block. The pressure of the injected material in the mold is very high and proper clamping needs to be provided to ensure that proper injection molding takes place. Remember I mentioned earlier that we select a specific tonnage of machine that decides the clamping force acting on the machine. This clamping force provided exerts an equal amount of force at all the ends of the machine. The diagram which you see on the left is the side view of the mold. You can see the runner, cavity and the mold block. And on the right, you can see the same mold block in an isometric view. In the first case, you can see the runner is at the center of the mold. So when the molten material is injected into the mold, there will be a force at the center of the mold blocks, which will try to separate the mold blocks from each other. This force is denoted by the letter F in the diagram. And since we don't want the mold blocks to get separated, an equal clamping force will be exerted equally from all ends to counteract the pressure of molten plastic. This clamping force is represented by the letter P, and the value for this will be calculated based on the formula for calculating the tonnage of the machine. So since the opposing force at the center is balanced by the clamping force at the ends, the first mold is said to be balanced and will function properly. Now let's look at the second case. Let's say we can't provide the gate location at the top and we have to provide the gate location at some other face. So if we provide a runner as shown in the second diagram, then the point at which the injected material creates an opposing force will also change, and it will be near the ends as shown in the right diagram. Now, as the opposing force is not at the center, one side of the mold will require a higher clamping force and the other side will require less clamping force. And since it is not possible to have different clamping forces at each end, there will be some points in the mold where the clamping force is too high or too low, and we can't have either of these cases. So this is called an unbalanced mold and we can't use this. So what else can we do to keep the mold balanced and also have the gate location at the same point as second case? In the third case, you can see that the size of the mold block itself is increased in order to keep the sprue at the center. So in this case, the molten material injected will exert an equal force on all ends, and the clamping force will also exert a constant equal force at all ends to counteract this force. And the mold will be balanced in this case. So the thing to note is that the sprue location should always be at the center of the mold. So for single cavity tools, we try to go for case 1 as it is balanced and the material cost and runner length is also less in case 1. But in case we can't go for case 1 due to gate location constraints, then we can go for case 3. In case of multi-cavity tools, we always go for case 3. Here you can add a second cavity to the same mold and have a 2-cavity mold.
If we have a part with a slot in the center, then we can place the gate location at the center of the part as shown by the blue arrow in the diagram, instead of outside the part as shown by the red arrow in the diagram. The blue arrow case is similar to case 1 which we saw in balancing, and the red arrow is similar to case 3 which we saw in balancing. So providing the inlet from the center will reduce the runner channel length and help in reducing costs of runner channels and also reduce material wastage. Another point to note is that generally a better surface finish will be given on the cavity side compared to the core side. Also, the draft angles on the cavity sides are more than the draft angles on the core side. This is done to ensure that the plastic does not stick to the walls of the cavity. If you remember the working of the mold, I had mentioned that the cavity side is fixed and the core side is moving for the 2-plate mold. So when the core moves away from the cavity after the part is formed, the part should come along with the core where it is ejected using the ejection pins. The part should not stick to the cavity walls when the core plate moves back. So to ensure that the part does not stick to the cavity, better surface finish and higher drafts are given on the cavity side. In the diagram, the polished grain 320 and medium glass blast are types of surface finish. The polished grain finish is a better surface finish compared to the glass blast. In the diagram shown, if we provide the gate location at the center over here, you can see that some regions of the mold will fill earlier compared to other regions. The walls nearest to the gate point will be filled first and the walls farthest from the gate point will fill last. But what if we want a uniform flow over the part? To achieve that, we can make use of flow leaders. Flow leaders are the specific regions in a part that are purposely made thicker to promote the flow of the material. The flow of material will increase in the regions of higher thickness, which will help us achieve an overall uniform flow of material. Now we will be looking at some of the defects which can occur in the molding process. Here all the defects are mentioned that I will be covering in this session. The first one we are looking at is the short shot. Now to acquire a component with correct dimensions, the molten material must completely fill the cavity region. But in some cases this does not happen. In the diagram you can see that there are some regions where the flow of material did not take place. So what you see here is the short shot. A short shot is the incomplete filling of the mold cavity which results in the production of an incomplete part. Now this can happen due to a number of reasons. It is possible that the amount of material injected into the mold itself is not sufficient to fill the entire mold, or it is also possible that the pressure of the injected material is not sufficient to flow through the entire cavity. If proper vents are not provided, then the air would be trapped in some regions and then the material might not be able to completely fill it. Also, if the size of the gates is very small, or in regions with thin cross sections, the material may freeze before filling the entire cavity region, resulting in a short shot. Flash is the excess material that you will find attached to your component. Now this can happen when the core and cavity plate do not close properly, or the injection pressure is too high and the material seeps outside the mold. To fix this issue, we have to do some post-processing operations which will increase the production time. When two molten material flow fronts meet at a specific point, it creates a visible partition in the surface. This defect is known as a weld line. The component is especially weaker in the weld line and will easily break if force is applied along this weld line. In the diagram below, you see how weld lines are formed by changing the position and number of gates. In the first case, you can see that a single gate is used at the edge. This will create a single weld line in the region opposite to the gate point. In the second diagram, you can see 4 gates are used, which led to creation of 4 weld lines. Now since weld line is a type of defect as the component is weaker along the weld line, but here case 2 is better than case 1. This is because the component will be a lot weaker along the single weld line in first case compared to the weld lines in the second case. This weld line formed in the first case is called as a weak weld line, and the weld line in the second case is called as strong weld line. In case 3, you can see that the position of the gate was changed such that no weld lines would be formed. So as far the strength of the component is considered, case 3 provides the best flow of material in cavity. However, due to customer requirements, it might not always be possible to give the gate point in that location. Now we will look at the sink marks. Sometimes due to the shrinkage of the material at areas with higher thickness, a small crater or depression is formed. So the customers are informed of any possible sink marks that may appear due to the current dimensions of the product. We usually see this effects around the ribs. The rib thickness is usually kept around 0.5 to 0.7 times the thickness of the part to reduce the chances of sink marks appearing. Sometimes during the molding process, air might be trapped between the molten material, which will result in the formation of blisters. It is also possible that the feed material used is not dry enough, and while heating the material, it results in formation of steam, creating pockets of trapped air. Blisters affect the component aesthetics and also weakens the component.
Now we will look at jetting. When the molten material is passed through the gate with a very high pressure, it is sometimes possible that instead of uniformly filling the cavity section, the flow will have a wavy snake-like pattern which you see here. This is not a desirable way of molten material filling the cavity, as this leads to weak parts and also many internal defects. So if we have a case where jetting may occur, then we can either increase the gate area or change the position of the gate, as you can see in this diagram, so that a more uniform flow occurs throughout the cavity. Here, as the material flows through the runner and the gate, due to the position of the gate, the material will completely fill the left region before moving on to the right part, and thus a more uniform flow will be achieved. Whether a change in the gate location will be needed or not to prevent jetting is usually found out by mold flow analysis, and then the mold designer has to design the gate accordingly.
In injection molded products, you will sometimes notice a charred or a burnt dark plastic region. This is called as a burn mark. This can happen when the temperature of the molten material injected is very high. Burn marks can also occur when the air trapped in the cavity overheats instead of escaping out of the system. So controlling the temperature of molten material and providing proper venting usually fixes this defect. Warpage is a defect in which the shape of the component deviates from the required shape. This happens when there is an uneven shrinkage of material which occurs due to uneven cooling of the material in the mold. There can be many reasons due to which warpage occurs. Some of the reasons could be non-uniform wall thickness in the cavity or improper cooling channels. In injection molded parts, you will sometimes notice that some regions have a better surface finish compared to other regions. This results in a visible gloss difference in the product. This can happen due to improper surface finish of the mold tool itself, or it can also occur due to shrinking differences, or there might even be an issue with the raw material being used. Hesitation is a defect in which the flow of material along a specific direction slows down or completely stops. In case 1 below, you can see that the material is not being filled in the rib section. This is because the molten material follows the path of least resistance and fills the region with more thickness first compared to regions with lower thickness. That is why this defect is most common in areas with ribs or other areas with lower thickness values. This defect can be avoided by providing proper gate locations, as you can see in the second diagram. Overpacking is a defect in which more material is concentrated in specific regions compared to other areas. In the diagram below, you can see that due to the positioning of the gate, more material is being concentrated on the left side compared to the right side of the part. This will result in non-uniform shrinkage of the material and also non-uniform density in the overall part. The selection of the right gate location should solve the issue of overpacking. Unbalanced flow. We say that the flow is unbalanced when some extremities of the mold fill earlier compared to others. If all the ends fill at the same time, then it is called a balanced flow. Unbalanced flow can result in many issues such as warpage, density differences, and higher cycle time. Flow leaders, which I mentioned in the previous section, can be used to acquire a more balanced flow throughout the mold. So in this session, we learnt about the machine tonnage. We saw the points that are taken into consideration by the DFM team before starting the mold design. And we also had a look at the defects which can occur during the molding process. And that's it for this session. Thank you for watching the video.